Hello, and this is the last chapter, the chapter 13. This chapter will talk about the manipulator. We'll see what is the manipulator and how can we run the manipulator. We will use the OpenManipulator as one of the models, and we'll run it using MoveIt. And in the end of the chapter, we'll look how the real robot becomes synchronized with the one in simulation space. Now we'll see how we can make a model of the manipulator layer in the simulation space. And this time, we'll use MoveIt to move it. So let's start from asking, what is a manipulator? Did you ever see this kind of instrument? You might see it at least once if you measured or have full interest on the robotics field. This is the first arm robot, or so-called the manipulator, in the world, and was made in 1961. This can be called as a grandfather of all existing manipulators. There are many types of manipulators: the cylindrical type, the polar coordinate type, the rectangular coordinate type, the horizontal articulated type, and the vertical articulated type. And among them, someone will choose rectangular coordinate type as the most familiar type of the manipulator, because most of the 3D printer are applying this type. But another someone will feel familiar with the vertical articulated type, since this type manipulators are doing the work in most of the product lines in the world. And we'll learn in this chapter using this type of manipulator. The picture shown in the left is a manipulator as a real product with vertical articulated type. There are 6 joints and the links that connect it joint to joint. And there are many existing applications. There are a mobile manipulator. If you put the manipulator on the top of a tree, for example, they can be called as mobile manipulator. And there are arms on the humanoids. And even we can expand the concept of the manipulator layer to the bipedal locomotion of humanoid robots. In the DARPA Robotics Challenge Final, there are 25 different shapes, functionalities of robots that has manipulators. The number of joints was different, the direction of joints was different, and so even the motion was different. Everything can become different as the purpose, the ideas are different. There are 3 elements needed for manipulator control: the sensing, the planning, and the action. The manipulator should detect the objects to grasp one of them or to avoid the objects, and to control the behavior. The controller should know how is the pose and how is the torque put in each joint by itself. Plus, before moving, they should make the trajectory of each joint or the motion planning. And to make this happen, the controller should control the joints based on the position, velocity, and the torque. Now, what we are going to watch is an example of the manipulator applications. In the simulation, a service robot brings the wagon to near the man and gives the juice to him. After the simulation, the service system was tested on the real situation with real robot. The robot plans something to do and grabs the wagon using depth cameras, controls by itself. Here includes the sensing, planning, and action. So, are you thinking the manipulator is easy to control? Perhaps no. I think that even who are good at manipulation will think that it is not easy to use. If you are very first at manipulation, and you are now going to make smooth motion, you should calculate every angles of joints based on the timeline, and you will have a difficult time with kinematics and dynamics. But everything was changed by the open sources, the ROS and the MoveIt. You saw that there are open source navigation package existing already, so your robot can have driving autonomy, very easy, nothing for purchase. And it was also happen in manipulation layer. ROS supports the model visualization via URDF, which is made up in XML format. You can upload the shape and structure of what you made under RViz in the gazebo. And even you can control the model in the gazebo, since there are plugins that supports the message communication and connects between the gazebo and ROS. You can basically put the models directly into the gazebo simulation space, putting some books, cups on the shelf, for example, and it makes you easy to test your manipulation and pick and place algorithm in that simulation. Also, there are a MoveIt, well-prepared library for manipulator. Your suffering will be unhelpful in handling the kinematics and dynamics actually. As you saw that the function for navigation is in the RViz, you can do the pick and place demo easily. But we should know the basic knowledges to use manipulation well. The manipulator can be described with 4 parts: the base, link, joint, and the end effector. The base is the part which will be fixed with the basement. So if the basement is a mobile robot, then the manipulator will be a mobile manipulator. And if the basement is a humanoid, then the manipulator will be the arm of the humanoid. The leg is the part which connects the base, joint, and the end effector. The joint is the part which will actually move or revolute. The step motor or the actuator will be one of the parts. And the last, the end effector, defines the goal of the manipulator. If you put a gripper on that part, the manipulator will work for something like pick and place. And if you put a painter, it will work for painting like the door on the car. The first thing you should know is the joint, and there are 6 types. Just think these as in common sense in robotics field. We'll mainly deal with revolve joint in the example. The second important thing is the degree of freedom. Let's think about the can. Put it somewhere in particular pose. It might be stand straight or might be lean towards somewhere. And this can be described with an axis X, Y, Z, and the revolution for each axis, the roll, pitch, and yaw. Now the object in this example can be posed freely on all positions and orientations, so it has 6 degrees of freedom. And the manipulator showing on the right side has 6 joints, and every joint has 1 degree of freedom. So the manipulator has 6 degrees of freedom at total. In fact, the degree of freedom shows how much the robot can handle the target object. The can on the left side can be posed in 6 degrees of freedom, so to grasp it very well, the manipulator should have at least 6 degrees of freedom. The third is to notice the difference between the workspace and the joint space. Here is an example. Let your robot grasp the specific object. You will order it by giving a position and orientation of the target. This is called a workspace. But the robot, which is built up with several joints and links, can find out the meaning of the position and orientation value. All values should be given in the angles for the robot control, and this is called joint space. So we need something like interpreter between 2 different spaces. there are forward and inverse kinematics, which is for geometric value transformation. Actually, there we has another way to move the robot, the dynamics. But in this chapter, we will focus on the kinematics, and we will see how the value can be changed. This is the forward kinematics. If the value of every joint is given, the forward kinematics will show where the end of the effector is in the XYZ coordinates, and the orientation also. Forward kinematics is very simple. Imagine that you bend every joint of your arm, each in specific angle, and see where your hand points out. Now you will notice that your hand will point out only one direction, and there are no more directions that can be pointed if all your joints are fixed in that situation. In other words, you can get only one value in the calculation. On the other hand, the inverse kinematics calculates each angles of the joints using given pose of the end effector, and will find multiple solutions in the calculation. Let's grab your right hand with your left hand to fix the pose of your hand. And you should fix the body at the same time. Then move your elbow. Can you see it? The angles of the joints can change, but the hand can be fixed. This means sometimes you will get more than one value of the joint angle. And therefore, there are special algorithms to solve it in specific conditions. So, congratulations, you're now a genius. You understood the core of the manipulation. What? You couldn't understand? In fact, you don't need to understand. We have moved it. This is the video taken in 2017. This shows all the robots which uses to move it. Here is Baxter from Rethink Robotics, the PR2 from Willow Garage, the one from Universal Robot, the Motorman from Yasukawa, another one from Universal Robot, the manipulation task with UAV, Atlas from Boston Dynamics in DARPA Robotics Challenge, the scene of the University Darmstadt, a robot from NASA, Thorman from Robotics, Hihiro from Kawasaki, and this is a Totobot tree with manipulation layer. the robot from Fetch Robotics. So all the systems use the sensing, planning, and action of the movement. To use the movement, you should give them information of link and joint. To make this simple, just think the link as a metal frame of the robot, and the joint is the axis and rotation. Physics stops the motor, so the relation will be like frame, rotation, and frame. The motor has a weight and appearance, so don't misunderstand that. The motor frame is also the link, not the joint. So the movement needs what kind of material and what kind of shape you will use to build a robot. And then, MoveIt wants to know how the frames are connected, and which direction will the frames be rotated, how much powerfully will they rotate, and where is the axis of the rotation, and so on. The ROS, MoveIt, and Gazebo uses different visualization formats, but they are almost the same. So just know what is URDF format, and then expand your knowledge. Let's start with 3-joint manipulator. This has 3 joints between 4 links connecting with each other. Make a package and an URDF file inside the package. We will put the sources in so that this can visualize the manipulator. And this is the code you should put in the URDF file. And from now, we'll see the details of each line. Let's see from the first link. We learned that MoveIt needs what kind of frame you are going to assemble, and these are the descriptions. The visual layer makes the appearance of the frame in the simulation space. The box size on Z-axis is 0.5, and to place their link exactly right on the base, the origin of Z-axis is set as 0.25, which is half of the box size. The collision layer is for taking the collision influence between the objects into account. You can set the values as same as the visual, but for safety, you can add extra volume as follows. The inertia layer is for calculating other physical things, like forces from gravity will be taken into account. Then let's see the second joint. There are only few things that you should fill in. Is a joint of revolution type? Which links are connected? What is the axis of rotation? And so on. So, after finishing to fill in the URDF file, you should check if the URDF is properly drawn. If the results show as follows, your URDF file must be correct. If there is no issue in the URDF, let's visualize what you fill in. The following runs 2 nodes, the Joint State Publisher node and Robot State Publisher node. They update the information filled in the URDF, and so the simulator subscribes it and visualize the models. Launch the launch file you've made and run the ROS. Click Add button on display and add robot model and TF. Try to change the joint angle values in Joint State Publisher window. Now you will notice that the links and joint moves to somewhere. And previously, we set the model of the frame as a box. But if you have a specific model that is drawn in design software, put the mesh in the simulation. Then let's see about the OpenManipulator. The basic frame of the OpenManipulator in the simulation is the same of what we have seen in previous step. But from now, we'll move it using trajectory generation and path planning by the algorithm inside the MoveIt. There are many manipulators in the world, but they are very expensive, and it is very difficult to customize its shape or modify the structure. The OpenManipulator comes out from the idea of using open source software and hardware, 3D printed parts, modularized actuators, to make cheap manipulator easier. There are already a few kinds of examples that are different on their shapes. They are available online. The software fully supports the drivers and even the kinematics for the actuator, the dynamic cell. Not only the ROS MoveIt, but also sophisticated examples that can be run in embedded level are supported. You can even put this onto the Totobot and build up mobile manipulation. All sources, all the details are provided in the following links. There are also the 3D model of the examples online, so use it also for 3D printing. To run the ROS package for your OpenManipulator, you need the following. Install all of them and go to the next page. So now we will see the running OpenManipulator under ROS. If you download the source, you can see these files. And now we will see the OpenManipulator running by ROS message. So we tested the manipulator under ROS and Gazebo. We have run manipulator by changing the angle of joints. But our goal is to make the robot move in a very clever and very smooth way. So now what we need to do is mixing the MoveIt to the simulation. The features were already described in the previous pages. MoveIt has all the elements of what a manipulator needs for move out. The sensing, the planning, and the action. Then we can guess, how can we use the MoveIt? Is it a library, so we can just import the library? MoveIt provides graphic user interface called MoveIt Setup Assistant to create the MoveIt package with the information you give. Run the command to run the MoveIt Setup Assistant. Then a window will appear. If there is a package already created, click the right button. But this tutorial assumes this is the first time using the MoveIt, so click the left. Now the wizard wants the model of the manipulator. Put the path of the target URDF or the Z row and click Load Files. This step is for checking the self-collision. As long as the simulation uses the rendered model, the overlap between two models will be self-collided. So the simulation should ignore those parts to avoid the collisions. And if you generate with high sampling density, the simulations after you will avoid the self-collisions very well, despite of huge computation time. The links on the tables are the parts that can be self-collided. This step is for extra joints. They are not in the URDF, but it's necessary for specific movements. But we'll skip this. This step is to add the planning groups. The planning will plan the trajectory in a group scale. Gripper isn't needed to be critically planned in this tutorial, so you don't need to add the parts of the gripper to the group. So make a group and choose the kinematic solver. We often use the KDL kinematics plugin. Click Add Joint to make the planning group. Join the parts into the group and save. So now it shows the group which includes 4 joints, and do the same to the parts of the grippers. And so finally the group should be 2. The next step is robot pose setting. Here what we set is specific pose of the manipulator. Just think this as a shortcut pose. And the next is for end effector setting. In this example, the end effector is a gripper, so this should be included in the gripper group. And the end tip link is the link 5, so the parent link should be the link 5 in this example. If your manipulator has a passive joint, then push the joint to the passive joint. But in this tutorial, we don't have any passive joint, so just skip this. Put your information in. Put the path of the package that will be created. Then click the Generate Package button. This is the end of the steps for movie package generation. So if there were no problems during the package creation, a package should be created. Do the following and run the movie demo. There are some kinds of plan libraries. To choose RRT Connect config default. Then drag and drop the end effector. And click Plan and Execute button. After that, see the movement of the manipulator. Now let's see the manipulator moving on the gazebo. And let's move the gripper. So we have seen all the movements that the manipulator can do in the simulation space. Now let's see how the real one can be synchronized with the simulator. Prepare the following instrument settings and do the next step. And the last thing is to build a mobile manipulator. The Tottlebot package has a URDF also. So to use them together, put the following into the Tottlebot's URDF. Then you can check it in the RViz like this. So this is what move it can do. We saw the tutorials without any touch for the kinematics and dynamics. All the stuffs are in the movement. And after this chapter, all the things is up to you. Let's study further and make a best robot together.